Okay, so in the discussion, last time we talked about abstract problem, how to find zeros of a general operator. In particular, this what we call the monotone operator. The simplest approach is the proximal method that we have seen before. Okay. So to solve this equation, in many cases, f is not directly invertible. So what we do is we build up this fixed point equation by introducing this identity operator. For example, if f is a matrix, think about if f is a linear operator, matrix may not be invertible. So but once we add this identity, it may be invertible. Okay, so we can invert this part and then build this fixed point equation. In fact, this is exactly the proximal operator that we have seen before. So this is called proximal point method. So iteratively apply the proximal operation. But this method only works when this f is simple. Simple in the sense that this inverse can be easily computed. Okay, this is the case for many simple functions, where the proximal operator can be easily computed. However, last time we see that for this saddle point problem that we have formulated, the corresponding f operator is very complicated. This f operator contains two big components. One is a linear equation, is a linear operator in x and lambda. The other is a nonlinear operator defined in terms of sub-differentials. So directly inverting this operator is not possible. Right? So this is very difficult to compute. However, we observe that this operator is a sum of two operators. Okay, the first one is a linear operator. It's very simple. Second one is sub-differential operator. It might be also simple if f and h are simple functions. Therefore, this motivates us to consider splitting this operator into two operators. So we start to consider the structures of this problem. So we formulate the problem as finding zeros of this sum of two operators, A and B. Well, A is the linear operator part, B is the sub-differential operator part. But the question is, for A and B, for each of these two smaller operators, we can compute this proximal mapping, or what we call the resolvent mapping, this inverse mapping. Later on, we will see how to compute that. Basically, this part, the resolvent operator of this part is proximal operator. And for this one, it's basically solving a linear equation. So it has an analytical solution. So for these two small operators, we can get their resolvent. However, we are looking at the resolvent of the sum of these two. So they are not directly related. So we need to think of a way to connect these three resolvent operators together. And this is given by this lemma. This lemma shows that finding a zero of sum of two operators, right? This is our original problem. We want to look for a point x that is a zero of sum of A plus B. And we know this equation, this inclusion equation is equivalent to this fixed point equation. It's the fixed point of the resolvent of A plus B. However, as we discussed before, the resolvent of A plus B is not easy to compute. But we can show that instead of considering this fixed point equation, we can consider a much more complicated fixed point equation that involves only the resolvent of A and the resolvent of B. So looking at the right-hand side is, so we have such a fixed point equation. Z is a fixed point of CA composite with CB. Well, CA and CB are the so-called Cayley operators defined as follows. So CA is 2 times RA minus identity. CB is 2 times RB minus identity. So these two operators only involve RA and RB. Only involve the individual smaller operators. So they are easy to compute. And this lemma shows that finding a zeros of this sum of two operators is equivalent to finding a fixed point of these two operators. And well, this x, the x on the left-hand side is defined as the resolvent operator of B applied to Z. So first you find out a fixed point Z. First you find out fixed point Z, and then how do you get x? Well, x is the resolvent operator RB applied to Z. Okay. So it's a bit complicated, but the good thing is that on the right-hand side, all the operators are about either RA or RB. We are not looking at, and this completely avoids this complicated operator, RA plus B. Okay. So we successfully split the resolvent of these two operators into smaller operators. So, but through a very complicated scheme. So this is kind of the trade-off. So next we will prove this lemma, which is a little bit tricky. So remember, the way we prove this trivial result, right? We start from the inclusion equation, and then we add an identity operator to both sides, and then this part can be invertible. Okay. So basically, we start from the original inclusion equation and start to add some terms to both sides to make them invertible, and then we end up with a fixed point equation. But this is a simple way to construct a fixed point equation that is not practical. So here we are going to prove this lemma. Well, this fixed point equation is more practical to compute in practice. So we will start from, it's actually easier to start from the end and go to the beginning. So we will start from the last line of proof. So we are looking for x that satisfies this inclusion property. Now what we do first. So first of all, this is equivalent. I can look at eta times ax plus eta times bx. Well, eta is bigger than 0. Okay, just multiplying both sides by a positive constant doesn't change the inclusion equation. And then I can add 2x to both sides. So it's 2x belongs to 2x plus eta bx plus eta ax. Okay, again, I'm just adding some terms to both sides. And why do I want to introduce 2x? Because now we have two operators. I want to add one x to each of them. That x serves as the identity operator. Okay? So we need to introduce two identities here. So that's why I add 2x. Okay, that's why we have this line. This line. And then we define z to be x plus eta bx. We define z tilde as x plus eta ax. Okay, these are the two auxiliary variables that we introduce. Basically, we will distribute these 2x to these two terms evenly. Okay. So one would be regarded as z, the other will be regarded as z tilde. Therefore, this equation, this entire equation is basically 2x is basically 2x equals to z plus z tilde. Okay. And z plus z tilde is what we have on the right hand side. So we have this equation, 2x equals to z plus z tilde. Well, z and z tilde are defined as follows. These are the definition of z and z tilde. Okay, and then and then we need to further introduce some slack variables. So 2x belongs to z plus z tilde. So up to now we have z and z tilde. Well, z, so let's write down everything we have. Well, z belongs to x plus eta bx. Z tilde belongs to x plus eta ax. So this is the equation that we built. And then from these two inclusion property, from these two, we get x is equal to RBZ and x equals to RAZ tilde. Right, by taking the inverse. Taking the inverse, invert the right hand side to the left hand side. After inversion, that is the definition of the resolvent operator. Right, so so we have these two. We have these two equations. Okay. And actually here x equals to x tilde. So it's x equals to x tilde. So this is basically 9.7, 9.7 A and C corresponds to these two equations. RBZ equals to x and RAZ tilde equals to x. Okay. And then I think it is easier to start from the conclusion and then go to this line. So let's start from this fixed point equation and see what we get. So the fixed point equation, we have two, CA, CB, Z equals to Z, where X equals to RBZ. Now, what is CA and CB? Let's go back to their definition. It's 2RA minus I composite with 2RB minus I, Z equals to Z. Okay, now let's just expand this equation carefully. It is not easy to go from here to here, but maybe easier go from the bottom to the top. So let's start from the conclusion and go back to the top. So by expanding this one, this is what? This is 2RBZ minus Z. And 2RBZ minus Z. And RBZ is X. RBZ is X. So this is 2RA minus I times 2X minus Z. Right, so we simplified things a little bit. And then we further expand it. So we get 4 times we get RBZ is X, right? Okay, and here's the thing. 2X minus Z is our Z tilde. Right, 2X minus Z is Z tilde. So here is basically 2RA minus I times Z tilde. That's our definition. We define Z tilde as 2X minus Z. Right, so here we use 2X minus Z equals Z tilde. And then here we have 2 times RA Z tilde minus z tilde equals to z. Okay. But RAZ tilde is x. This is x. So this is 2x minus z tilde equals to z. And this is consistent of what we have, right? So to continue the proof, right? So we were here. We have 2x belongs to z plus z tilde. Well, z tilde defined in this way, and x basically x is given by RAZ, RBZ, and RAZ tilde. To continue the proof, you actually start from this line and go top. You will reach at this point. So you can go in from the bottom to the top. The last line is what we have before, and then this line, right? We have it here. We have it here. And then x equals to RAZ tilde. So this x equals to RAZ tilde. And then this can be organized in this way. And moreover, z tilde is given by 2x minus z, right? And furthermore, x is given by RBZ. So eventually we get to this fixed point equation. Right? Eventually we get to this fixed point equation. So it is not easy to get. It is not easy to construct such a fixed point. Very, very tricky. Very tricky. So this is an alternative way to find. It's an alternative fixed point equation to find zeros of sum of two operators. Now, ideally, what you do in practice is, given this fixed point equation, you can run an iterative algorithm, right? You set ZT plus 1 equals to CACB applied to ZT, and you iteratively apply it. Okay. Well, CA, CB, they can be computed easily because I and RB, they are these two proximal mappings, they can be done relatively easily. Okay, so this fixed point equation, intuitively we can run it. Once this equation converges, okay, to some z, your final solution is this one. So x is your final solution. It's given by the resolvent, the proximal mapping, the resolvent of B applied to Z. So that is the final solution. Okay, so this is called operator splitting, operator splitting algorithms. And there's a book about that. But this is one of the most important ideas. I think if you look at optimization problems, many of them will fall into this framework. So this allows us to split these two operators, A plus B, into A and B separately, but through these very complicated Cayley operators. Okay, so the proof, and this one will lead to our algorithm design. Okay, so the question is how to find, once we have this fixed point equation, how do we find such a fixed point? Well, a very simple idea is to run this fixed point iteration. This is what we just described. Okay, just run this iteration repeatedly. Hopefully it will converge. However, unfortunately, it may not converge in general for this fixed point equation. So this motivates us to design this so-called Douglas Rankford splitting algorithm. Well, it's basically a damped version of this fixed point equation. So instead of directly applying the fixed point equation, we do 1/2 identity plus the fixed point plus this operator. This is a damped version because, well, first of all, you can imagine this fixed point equation may not converge because this operator, it may not be that stable, right? It's a very complicated operator, it's compositions. But here, again, we see this idea. We add an identity operator. By adding an identity operator, we can kind of stabilize the spectrum. Well, we can control the spectrum of this operator and stabilize this algorithm. And the idea is that we can start from this fixed point equation. Can start from this fixed point equation, and I can move 1/2. Actually, I can add a z divided by 2, and then divided by 2 on both sides. They are equivalent. They are equivalent because if you subtract, actually, it's this one. Yeah, they are equivalent. I can add a z but divided by 2 because z subtracts z over 2 is z over 2, and then this 1 over 2 will be canceled out. Right? So this is equivalent. This is equivalent to this fixed point equation. And then this motivates us to consider this damped version. So the left-hand side is our next iteration, and then the right-hand side is our previous iteration. Right. So we have this damped fixed point iteration inspired by the original fixed point iteration. And it can be shown that this, by modifying the fixed point iteration in this way, this iteration can converge to the solution. Can converge to the solution, to the zeros of this inclusion equation. So we call this algorithm the Douglas Rankford splitting algorithm. It's a very, very important algorithm in the control area and optimization area. And this update rule can be explicitly written in terms of RA and RB, right? Because in this update rule, these two operators are very complicated, right? And this is to explicitly write down all the small steps in order to implement this update rule. Okay? So many of the steps are to basically calculate these two operators, because they are, each of them is 2 times the resolvent minus identity. So eventually, after some equivalent simplifications, there are 2 versions of this algorithm, but I think this one would look much easier. This is the algorithm. Right. Start from ZT, do a proximal mapping of B, you get an intermediate result. And then you compute this variable 2 times your intermediate result subtracts the ZT. Okay, and then apply a resolvent of A. And then you get another intermediate result. And eventually, ZT plus this result minus the previous result gives you next ZT, ZT plus 1. So you do this, you run these 3 iterations, 3 steps iteratively. Eventually, this Z will converge to the fixed point of this equation. Right? Z will converge to the fixed point, and X will converge to such a solution. X will converge to this solution. Okay, so this is the final algorithm. And you can see in this algorithm, we only need to compute these 2 operators. Okay, they are proximal operators associated with A and B. So in many cases, are very simple and easy to compute. Okay, and finally, we can go back to our original problem. Go back to our original problem, the saddle point problem. And just to recall this problem formulation, we start from this minimization problem. Okay? We're looking at this minimization problem, and we come up with this saddle point formulation. And the nice thing about saddle point formulation is that this A is no longer involved in H. A is inside this bilinear term. Okay, now what about how to solve this saddle point problem? We look at these optimality conditions. Okay, and turns out that this optimality condition is to find a 0 of this big operator F. Find a 0 of this big operator F. However, this is not possible to do. So what we do, we can consider apply the Douglas rank for splitting. We split this operator into operator A, a linear operator, plus operator B. Okay. We have these 2, we then plug it into the Douglas rank for splitting algorithm. So this is what we do next. Okay, we have this problem. We then apply the Douglas rank for splitting to 9.5. What is 9.5? This one. Okay. We want to find a 0 of sum of these 2 operators. Okay. So eventually, we get this algorithm. Okay. So let's look at this algorithm. First 2 steps are proximal mappings. Right? Proximal mapping. Okay, if you give me a PT and a QT, right? So they will be updated later. Right? Give me a PT, QT, I compute the proximal mapping of F and H conjugate. Now, suppose F and H are relatively simple. We can compute their proximal mapping. Right? Then these 2 steps can be implemented. In particular, proximal mapping of H conjugate by the Moreau decomposition is QT minus the proximal mapping of H. Okay, so these 2 can be done. And then these 2 steps is to compute the resolvent of the first operator, that linear operator. So it corresponds to solving a linear equation. It's a linear update. This can be done because this matrix is an invertible matrix. Identity on the diagonal, eta is very small, so it can be invertible. Okay, so this step can be done. After that, we simply update P and Q according to this update rule. So this is the Douglas-Rankford splitting algorithm applied to this saddle point problem. Applied to the saddle point problem. So you see, we completely avoid computing the proximal mapping of F plus H. It only involves a very simple proximal mappings. And they are computable. And here's one example to illustrate this idea. The problem we're looking at is to minimize X, minimize this objective function, which is the first term is L2 norm of X, the second term is gamma times AX minus B to the L1 norm. Right. This is a very difficult problem. It's different from the L1 lasso problem that we are looking at. So we can look at the compressed sensing of the lasso problem is, you remember, is minimize X. L1 norm plus this is what we did in the one of the homework problems. When we do proximal gradient descent, we apply proximal gradient descent to solve this problem. This is a relatively easier problem because this term is differentiable. And then this term is non-differentiable, but we can do the proximal mapping. Right? So we do proximal gradient. We can do the proximal gradient update. But this problem is very different. And this problem is to minimize L2 norm of X plus AX minus B. The AX minus B is like the residual error, the L1 norm of the error, right? So you see both of the terms are not differentiable, are not smooth everywhere. So it's we cannot apply proximal gradient here. Okay. And in fact, these two problems, they are looking at different, they are completely different models. The first lasso formulation, okay, we are doing a least mean square. This part is least mean square, but then we are looking for a sparse solution. We want our solution X to be sparse by penalized L1 norm. So in the end, when you do proximal gradient, the proximal operator will truncate this variable and make it sparse. So we're looking for a sparse solution. But the second one, we put L1 norm to the error part. This is in statistics. This is to this L1 norm is much more robust to outliers. When your data AX minus B, when the data is corrupted by outlier noise, then it is much better to use L1 norm than the least mean square solution. So in the second formulation, we are looking for a solution that we penalize the L2 norm of the solution. Right? So we want a solution that has a relatively small L2 norm, but more importantly, we are by using the L1 norm, we are trying to remove some outliers in the data. Your AX minus B, this AX equals to B. This equation may be corrupted by some outliers. right? So this really depends on your understanding of your underlying application, and then you will build a corresponding model. Okay. So this problem very hard to solve because of this term. L1 norm is not differentiable, and the inside this matrix A couples all the coordinates of X, so it makes things very complicated. But it falls into our framework, right? This is Fx, this is G Ax, and G is the L1 norm, F is the L2 norm. These two are very simple functions. We can compute their proximal mapping. So this exactly falls into the Douglas rank for splitting algorithm. So we just apply this algorithm. We can directly apply the Douglas rank for splitting algorithm. And then numerically, these two are the Douglas Rankford. I think the red one is what we are talking about, the primal dual Douglas Rankford split. Converges very fast. ADMM is the algorithm that we'll talk about later. Okay. And this is another example. Very popular model in image processing. Kx minus b. This is like again, we put L1 norm just to make it robust to outlier noise. Right? But Kx minus b, you can view it as a deblur. Yes, in image processing, this is called image deconvolution or image deblurring. So this image is X. Well, K is a linear process. Like sometimes, if the image is blurred, then that blurring process can be described by K. And then this part is the structure of the images. This D times X is usually it is the total variation norm. So basically, for images, we know that most part of the images are smooth. The pixel values are very similar, and the only change will be at the boundary points. So this dx will extract those boundary points. Okay, so we focus on the boundary points. So this optimization problem, again, is very hard to solve because of the L1 norm and this linear mapping, and also this penalty term. So we can formulate it into this framework, fx plus g times ax, where, and moreover, we have a constraint for images. Suppose we scale the values between 0 and 1, so there's a constraint. And then, so we will formulate this entire problem into fx plus g of ax. Well, fx is the indicator of this constraint. Fx is basically handling this constraint. It's indicator function of the constraint. G, this part, will model the entire objective function. So G y1, y2 equals to L1 norm plus L2 norm, plus this variation norm. And this A is a concatenation of K and D. Okay, so K is applied to y1, D is applied to y2, basically. And then for this one, the proximal mapping of F is easy to compute. It's essentially the projection onto this interval. And also the proximal mapping for this G Well, it may not be that simple, but I think it is also separable with regard to the coordinates. So there are some analytical expressions for that. So we can still model the problem in this way. So again, Douglas rank for splitting can be applied here. Okay. So you see in all these problems, we have two terms that are not differentiable and non-smooth, and maybe coupled with matrices. So it is the classic proximal gradient method does not apply. Okay, so I think that's everything for this lecture. So we talk about several algorithms: dual proximal gradient, primal dual proximal gradient, and Douglas rank for splitting. I think the key idea, the most important thing is this primal dual formulation. How do we starting from the primal problem? How do we construct and get to the dual formulation by introducing the Lagrangian multiplier? Okay, max, min, max. This is a very important idea in optimizing that theory. Okay. And the next lecture would be about alternating direction method of multipliers. This is a very popular algorithm in machine learning and many other application domains. So we can briefly introduce this the main idea first. Now we can briefly look at the main ideas. So let's look at the problem formulation today. So in the previous, in the lecture 8, we were looking at this problem. Minimize fx plus h ax. Well, it is essentially, let's look at the second one. This one is clear. Minimize fx plus hz. Well, x and z are coupled through this linear equation. Okay. So you see we have such a linear coupling. In lecture 9, we will be looking at a more general problem. f1x plus f2z. Again, this is similar to the f plus g, but the coupling is more complicated. It's ax plus bz equals to b. Okay, so it is more general compared to here. We only have ax equals to z, right? So it's a very simple coupling. A is applied to x, z is an identity, simply z. But here is ax plus b times z, right, equals to b. So this coupling is more complicated. Well, we assume f1, f2 are convex and their proximal mapping is easy to compute. In general, you can also apply Douglas rank for splitting to solve this problem. You just need to write down set of one formulation and just figure out the operators A and B. But here we will do it in a different way. And the technique that we are going to introduce is the augmented Lagrangian method. So let's first look at how we reformulate the problem. So again, we formulate this dual formulation, which is basically the objective function value plus this linear term. Lambda is the Lagrangian multiplier, and then we have that equality constraint is put here. So this entire function is called the Lagrangian function. And then for the inner problem, it's minimized over x and z. So again, we will leverage the definition of conjugate function to rewrite the inner minimization as using the terminology of conjugate functions. So you can check that by definition of conjugate function, the inner part can be written in this conjugate form. It's just by definition of conjugate function. And then lastly, we will change maximization to minimization by adding a negative sign. So we get rid of all the negative signs outside. So essentially, this is the dual problem. Dual problem is a primal problem. So this is a dual problem. And for this dual problem, we can apply the proximal point method to solve it in principle. Because the dual problem is this conjugate function may not be differentiable. So if you view the entire thing as a function of lambda, we can apply proximal point. And this is the proximal point update. Basically, in every iteration, we solve such a subproblem. Okay. This function is regularized by a quadratic term, lambda minus lambda t squared. This is like the definition, again, like the definition of proximal mapping. It's the proximal mapping associated with this function evaluated at lambda t. Okay, so this is the proximal point method applied to the dual problem. And it turns out that this update rule, again, because it involves the conjugate form, right? So we can rewrite it more explicitly using the primal function, primal definition of the function. Okay. So, and I will skip this part, but eventually you can show that this single update rule is equivalent to this two-step process. Okay. But in step one, we are looking at solving a subproblem regularized by a quadratic term. And in step two, we are updating this lambda. So this is called the augmented Lagrangian method. Basically, this is the augmented Lagrangian. And then we update the multiplier. So there is a very interesting connection between this. This is like the primal dual updates. The first update is primal update, and the second update is dual update. But this is essentially can be viewed as applying a certain optimization method to the dual problem. Okay. So there's always a very interesting, very close connection between this primal dual updates and the dual formulation. So, however, let's look at this 10.1, this update proof. So, do you think it is easy to implement in practice? So, given that F1 and F2 are simple functions, I suppose F1 and F2 they are relatively simple, and proximal mapping can be computed. Now, for this algorithm, the most important update is the first one. Right? So can we solve? Is it easy to solve this problem in practice? It's F1x plus F2z plus this quadratic term. Is there a way to solve it? Like, for example, using proximal mapping or
we have to simplify it first.
Yeah, you see, the nice thing is that these minimizations over x and z, and they are separate, they are different parameters, right? But this quadratic term makes things coupled because of a and b, right? For example, if we don't have this quadratic term, imagine if you don't have this term, then this problem is very simple. I just minimize f1x separately, minimize f2x, f2z separately. But now this quadratic term, inside this quadratic term, we have a times x plus b times z. So this a and b will couple all the coordinates in x and z. So then the entire problem, all the coordinates between x and z, everything will be coupled together. So this solving the first equation, solving the first problem is not that easy. We may need to implement another algorithm to solve it. We will need another algorithm to solve this problem. And that algorithm may be very difficult to find because of this coupling. So this is a simple idea to motivate introducing this augmented Lagrangian methods. But we can see if we directly apply proximal point to dual formulation, the resulting algorithm, it may converge theoretically, but it's very hard to implement in practice. And this part is the proof for showing the equivalence of these two. Okay, the proximal point applied to the dual updates, it can be rewritten into these two update steps. But basically, I think we have seen something similar before. Basically, you just follow the definition of conjugate function. So I will not. Well, we can briefly look at the logic. We start from the proximal point update for the dual formulation, and the optimality condition is given as follows. So it's basically 0 must belongs to the subgradient of the right-hand side. Now the subgradient takes this form, basically subgradient And then we need to utilize the conjugate subgradient theorem to characterize the subgradient of the conjugate function. Okay. And they can be characterized in the following two updates. So I will not go into the details. But you can see from this optimatic condition, we have lambda t plus 1, lambda t, right? So once you rearrange these two terms, you have lambda t plus 1 on the left-hand side, lambda t on the right-hand side. And then these two terms, you use conjugate subgradient theorem to characterize. Okay. So this is the augmented Lagrangian method. It's essentially proximal point applied to the dual problem. And for this method, you can clearly see the primal dual updates. The first step is primal step. Because we are fixing the lambda, we are optimizing over x and z. Second step, we are fixing x and z, updating the lambda. So it's the dual step, dual updates. And in fact, these two updates can be interpreted as alternating between optimizations of this augmented Lagrangian function. I think we don't need this part. So look at this this entire function. The first three terms is the Lagrangian function because it's objective function f1 plus f2 plus the inner product term, and the Lagrangian multiplier with this linear coupling constraint. So the first three is actually the Lagrangian function, but we augment it by adding this an extra penalty term. And this extra penalty term penalizes the violation of this equality constraint. Because rho over 2, the L2 square of this constraint violation. So we call this augment. That's how we call it, augmented Lagrangian function. This is the Lagrangian function augmented by this extra penalty term. And then these two steps is basically alternatively optimizing this augmented Lagrangian function among different variables. For example, the first step is basically once we fix the lambda, we minimize over x and z. Okay, and then these two terms, the last two terms, you can combine them together. You can complete this square term. Okay, you can put these two together as a big square term. So this will lead to the first primal update. So it's essentially fixing lambda, optimizing this augmented Lagrangian function over x and z. And the dual step is fix x and z, optimizing over lambda. That is exactly this update. Because this is a quadratic once you fix x and z, the only term with regard to lambda is here. Right? So it's basically, you can view it as a kind of gradient method applied to lambda. So the primal step, dual step, they are just alternatively optimizing the augmented Lagrangian function. And this method is, in many cases, is of theoretical interest, but we almost never use it in practice because of these two issues. The primal update is often very expensive. Solving this problem may need another algorithm, and that algorithm may take expensive steps to solve. Solving this problem is as expensive as solving the original problem. And the second thing is that because of this coupling, the minimization of x and z cannot be carried out separately. Okay? The first two terms, they are separate. X is here, z is there, but the last term couples everything together. So that makes the problem very complicated. Yeah. And I think for the next lecture, we can we'll talk about improved version of this alternating this ALM method, augmented Lagrangian method. Okay. So this ADMM alternating direction method of multipliers is a very important algorithm to solve this type of problems. It starts from the augmented Lagrangian method. Yeah, the idea is actually very simple. In the ALM method, we update x and z simultaneously. So in this primal step, we want to minimize x and z simultaneously. So that's why the problem is very complicated. But ADMM is very simple, very straightforward idea. Why don't we just update these two variables alternatively or sequentially? Right. So we further in ADMM, we further decompose the primal updates into two smaller updates. The first update, we only update x. We fix z, only update x. And then we fix x, only update z. Right, so we decompose the primal update into two separate updates, one on x, one on z, and then the dual update is the same. So it's a very straightforward idea. But we have to justify this this modification because sometimes if you simply do the optimization sequentially, it may not converge. But by doing so, the problem can be much simplified because in every of these updates, once you fix z, we are only looking at an optimization problem associated with one of the objective functions. For example, when we optimize x, we are only looking at x1. And this is something like the approximate mapping. When we look at z, we are only looking at f2. And again, this can be done by proximal mapping or some other methods. And so each of the sub-problem is much simplified. Okay. So I think we will leave the discussion to the next lecture, and we will have some proof, convergence proof. And one of the applications is related to one of our projects called robust PCA. Okay. So this one is related to, let's see, almost 6 or 7. Okay, homework 7 is the accelerated method. Yes, homework 8 about this is a final project. It's actually a big project. It's about video surveillance. By solving this, I give you a video. The goal is to extract the moving object in the video. It's unsupervised learning. Okay. You are not given any other instructions, only the video. And then we built such a robust PCM model, which is to extract both the stationary backgrounds and the moving object. So we will talk more about this model in the next lecture. And then for this homework, we are going to basically the ADMM method will be applied to solve this problem. This is the nuclear norm of a matrix. This is L1 norm of matrix. And the data, I will give you a data set. It's basically a small video and contains this many images. And we will follow the instructions to implement the ADMM method to solve this problem. Okay, so I think I will stop here today, and I will see you guys next week. So if you have any questions regarding this final project, feel free to talk to me. And we will discuss this project in detail next time after we finish this lecture.
Thank you.
You guys, see you next week.